this video is going to take quite a bit longer since I'm going to have to sketch a graph, and I'm using a mouse to draw with here. And also, I've left out real roots here. Now, I'm not sure you really even need to put real here, because if these were complex solutions, the notion of a ceiling I don't think applies to complex numbers. But just for emphasis, I'll say we're given that we have 3 distinct real roots, okay? Now, this is a cubic, so let's sketch a picture of this thing, sketch a graph, and see what type of insights that graph will yield. Okay, so let's just do the, I guess, XY. Let me make this big enough. So XY axis here, Cartesian axis. Now, one thing for sure is the graph passes through this point 0, 11. Okay, that's the easiest point to get, right? On the graph, 0, 11. Now, remember college algebra, pre-calculus, they would teach you about this notion of end behavior. Well, the cubing function looks like this, right? Remember? It looks something like this. I'm not going to sketch it like that. And so that's what we have right here. We have a function that's going to have to come up and cross somewhere. That will explain one of the zeros. It's going to have to intercept right there. And then to have its end behavior, it's going to have to look something like this, right? So you see, notice that this behavior here and here is cubic. Okay, so you see we have a root right here, a root right here, and we have no idea what these values are. But we're supposed to find the sum of the ceilings, okay? So if those roots are a, like for example, if this would be a comma 0 right here, call that a comma 0, this would be b comma 0 and c comma 0. What we're actually looking for here, folks, is the sum of the ceilings. So we're looking for the sum of the ceiling, folks. The SMO problem, I think, was floor. Okay, so A plus ceiling of B plus ceiling of C. Now, you can almost be certain these are irrational zeros, because you can try the rational root theorem. There's not many tries, but none of them work. Okay, so there's no rational solutions by the rational root result, and so that means they got to be irrational. All right. Now, so let's talk a little bit about this this guy right here. Let's say let's do the ceiling of, I don't know, 4.1. Okay, well, that would be equal to 5 based on this definition. Okay, because 4.1 is between, if you look at this definition, 4.1 is 4 less than 4.1. Less than or equal to 5, right? Okay, so that's an example with a positive number. Now, we are going to have one negative answer, and so we'll look at how the ceiling function handles that when we get there. But notice we have sign changes right here. Like you see, you have plus on this side, but you have minus on this side, right? Oh, that's supposed to be a minus, folks. Sorry, a minus sign right there. So the sign of the graph is negative. God, okay, it's negative down here. Sorry, negative here and positive here. Okay. Okay. Now right here it reverses. You have positive values for the value of the graph, and then negative values here. God, I'm just retarded, completely retarded here. Negative. Okay, then right here you have negative going to positive, right? That was bad. That was politically, when I was young, retarded was okay. Now it's considered a pejorative, I think. Okay, but so we're looking for sign changes, and we know we're looking for 3 sign changes, right? From negative to positive, from positive to negative, and from negative to positive, right? And so what you do, you have to evaluate the function. You have to evaluate the function. And we have our first sign change. I started conveniently at 5. Okay, I probably, just to make it a real problem, I should have tried 6, but I'd already kind of sketched the graph a little bit more precisely, you know, using technology, I'll admit it. But I probably, just to make this an honest problem, probably should start at 6. But notice right here, we do have a sign change. So we know that our A, we'll call it A, is between less than or equal to 5, right? And then like that. Okay. Now, I may not have labeled it the same way on the graph. I probably didn't, but we'll call A that one. Okay. So that means that the ceiling, I think I did mislabel it, but anyway, you get the picture. It doesn't make any difference that really. The ceiling is equal to 5 for A, right? Because you see, folks, we did have a sign change. We went from positive to negative. Now, y'all, that would, let's go back up to the graph. That would be the one right here, from positive to negative, right? And again, y'all, to make this an honest problem, so to speak, I should have started at a higher number and waited for the sign change to occur. Okay, now there's no sign change from here to here, from here to here, from here to here, but now we can call this one B. B is between 1 and 2. You know, by the way, that's the fancy name for this in calculus is the intermediate value theorem. All these functions the kids deal with all the time are continuous, so they no need to resort to something that's obvious, you know, and kind of a deep proof from calculus, the IVT, the intermediate value theorem. You know, it's something that people understand it without having to give it a sophisticated name or even reference calculus. Okay, but we have B, we have a sign change happening between these numbers right here, and again, that would be you're going from minus to plus, right? So you're right here, all right? And again, I definitely mislabeled this right here. This should be A over here as far as the letters I'm using here. Okay. Now, so what does that mean? That means the ceiling of B is, you know, I'm looking for a platform where I can write faster. I use the mouse. I've been doing that forever, but I've never trusted other platforms. This at least works. It's cumbersome. It's not what it was intended. It's just for somebody who's working in Word, right? And not intended for a presentation, so it is slower. Now, so we have the ceiling of B is equal to 2. Now, okay, let's move along here. Now, notice we only have to find 3 sign changes, all right? And we get our other sign change between minus 1 and minus 2, okay? And so let's see, which one comes first? Minus 2? Yep. Minus 2 is less than, what letters are we using now? C? Okay. And it's less than, or whoops, yeah, let me erase, folks. Okay, so we have minus 2 is less than C. I didn't need to erase, did I? Okay, is less than or equal to negative 1. And this is just how the ceiling function is defined. So that means the floor of C is negative 1. See, it works the same way. Not the floor, the ceiling. Okay, so it's negative 1. My bad, folks. Minus 1 right there. And so, folks, right here, we can see the sum of the ceilings of the roots without knowing what they are. We know where they are, but the ceiling traps things between intervals, you know. So, between 2 integers, excuse me. So this sum looks like it's 5 plus 2 equals 6 is what I got, folks. Yeah, I did double check, but I'm getting to the point where even when I double check, I catch mistakes, and sometimes polite commenters let me know about that. So this is the answer, folks. It's -6 is what, I mean +6 is what I got here. Okay. And again here, I sketched this graph by hand, but I really didn't have any idea where this was, and I did graph it via Desmos or something just to see. And so this kind of betrays that. An honest approach here that's not graphical, you'd probably start further out and wait for the sign change. And I guess there's ways to get bounds on the roots based on this constant, but I don't know much about that, or I didn't want to mess with that too much. But anyway, the sum of the ceilings is 6, and we'll circle the answer again. Okay, let's have a piece of toast.